Imagine a cosmic neighbor so quiet you'd never know it was there. No fireworks, no bright X-rays, no drama. Yet its gravity quietly tugs at a visible star like an invisible dance partner. Now imagine that every rulebook we've written about how black holes are born says something like, "That scene shouldn't happen here." According to the standard story of stellar evolution, nearby, quiet black holes like this are improbable. And yet, thanks to precision surveys and a bit of detective work, the universe keeps handing astronomers exactly those awkward, rule-breaking cases. The result? A growing pile of evidence that our textbook picture may be incomplete, and that the cosmos likes silent surprises. Let's clear one thing up. The galaxy almost certainly contains millions of stellar-mass black holes. Statistically, some should be relatively close to us. What shouldn't exist, though, is a quiet black hole in a calm, ordinary stellar neighborhood that shows no signs of having been born in the textbook way. A loud supernova that kicks the newborn object out of the neighborhood or contaminates its nearby companion. Why would that be odd? Because the standard route to make a stellar black hole is dramatic. You need a very massive star. It burns fast, and its final collapse usually involves an explosion, a supernova, that is messy and asymmetric. Those asymmetries can kick the compact remnant at hundreds of kilometers per second, sending it on a wild ride away from its birthplace. So finding a black hole that's just sitting there, quietly co-orbiting a normal star, challenges either our readings of the system, our assumptions about how black holes are born and behave. Astronomers used to rely on fireworks to find black holes, X-ray flares from gas spiraling in, radio jets, bright accretion signatures. But the quiet ones hide. Modern discoveries come from precision measurement of motion, watching a visible star wobble, speed up and slow down, or trace a tiny ellipse on the sky caused by an unseen companion. That's astrometry and Doppler spectroscopy in action. The same physical tricks you use to infer an invisible dance partner by watching the person on the floor. The European Space Agency's Gaia mission has been transformational here. By mapping stellar positions and velocities with exquisite precision, Gaia has revealed gravitational tugs that point to dormant, non-accreting black holes. The silent discovery method. A visible star's motion tells us a lot. Measure its changing radial velocity, the Doppler shift, measure its tiny positional wobble, astrometry, and, crucially, get a good distance. Combine those, and you can compute the hidden companion's mass. If the invisible object is heavier than the maximum mass for a neutron star and emits no light, the conclusion is robust, a black hole. This is the exact approach that led teams to announce dormant, nearby black holes. These aren't the X-ray beacons we're used to, they're gravitational fingerprints. And when multiple independent instruments confirm the same wobble, Gaia astrometry plus ground-based radial velocities, the case strengthens. Mistakes, rechecks, and humility, the pound one lesson. Not every eyebrow-raising claim survives scrutiny. A famous example is the oddball system known as Pound 1, which at first glance seemed to host an impossibly massive, tens of solar masses, black hole in our stellar backyard. That claim sparked excitement and panic because such a heavy object, quiet and nearby, didn't fit easy formation paths. But subsequent reanalyses showed the system's visible star was mischaracterized. The black hole interpretation didn't hold up under better data and modeling. Pound 1 is a cautionary tale. Small measurement errors and mistaken stellar classifications can produce impossible black holes on paper. It taught astronomers to be extra rigorous about distances, spectral types, and alternative explanations like two faint stars masquerading as one invisible heavy object. The true oddballs that survived scrutiny, Gaia BH1 and BH3. Contrast Pound 1's retreat with discoveries that stuck. Teams using Gaia data, confirmed with independent spectra from big telescopes, have identified dormant black holes that truly match the quiet neighbor profile, an ordinary star with an unseen, fairly massive companion whose mass can't be explained by planets or faint stars. The discovery, dubbed Gaia BH1, announced in 2022, and the later, heavier Gaia BH3, announced in 2024, are great examples. These systems were flagged by astrometric wobble and then followed up spectroscopically, and their inferred companion masses placed them in the black hole regime while showing little to no accretion luminosity. In short, they look like black holes hiding in plain sight. If you accept that the data are good, two physically separate resolutions explain a quiet, nearby black hole. The black hole was born quietly. Not every massive star explodes like a movie supernova. Some models and searches point to failed supernovae or direct collapse events. The star's core collapses and, instead of generating a bright explosion, the outer layers fall inward or are ejected faintly, and the star essentially vanishes. Observational programs that watch nearby galaxies for stars that disappear without a supernova have found candidates consistent with this scenario. One well-studied case, the object catalogued as N6946BH1, brightened briefly and then faded, leaving an infrared glow but no optical star. Long-term follow-up suggests the visible progenitor did not reappear, consistent with the idea that it collapsed directly into a black hole rather than exploding. If direct collapse happens with some frequency, it naturally explains why some black holes stay put. They never received a violent kick. The black hole formed elsewhere and quietly arrived. Alternate histories exist. A compact object could form in a cluster, receive a big kick, and later sweep through and capture a companion, or otherwise end up where we now observe it. Or, more exotically, maybe some black holes have origins outside the usual stellar collapse story. More on that in a moment. Point is, a calm present-day orbit doesn't automatically reflect a calm birth. Reconstructing the past requires careful kinematic work, measuring the system's motion relative to the galaxy, and checking whether it behaves like a native of its surroundings or an interloper. Gravitational microlensing surveys, where a foreground compact mass temporarily magnifies the light of a background star, have produced candidate isolated black holes. These are cases where the lensing event's duration and astrometric signature point to a compact object with black hole-like mass. However, microlensing interpretation is subtle. Modeling degeneracies and nearby bright stars can bias results, and teams have reanalyzed odd cases to differing conclusions. Even with that messiness, microlensing remains a powerful independent probe of the invisible population because it doesn't rely on a black hole having a luminous companion. Population modeling using Gaia's expected yield also points to a future in which dozens or hundreds of detached black hole plus luminous star binaries are detectable. The trick is that you need both precise astrometry and careful follow-up spectroscopy to rule out imposters. In other words, the observational tools are finally getting good enough that we should expect to stop being surprised by quiet neighbors and start counting them. 1. Black hole formation is not a single-mode process. If direct collapse is common, then many black holes are born without the dramatic expulsions we assumed. That affects predicted natal kicks, black hole velocities, and where we expect black holes to be located in the galaxy. The observational candidate N6946BH1 and LBT survey results make direct collapse a live possibility. 2. We may have a serious detection bias. For decades, we found black holes the loud way in X-rays and built population models around that. Precision astrometry is exposing a quiet majority that we undercounted, that matters both for stellar evolution theory and for estimating how many black holes might eventually merge and produce gravitational waves. 3. We need humility in single-case claims. The Pound 1 episode shows how a single misunderstood spectrum or bad distance can produce a headline that later collapses. Independent methods and reanalyzes are essential. 4. Primordial or exotic origins remain a remote but testable idea. For especially strange objects, those with odd masses or kinematics that are impossible to explain via stellar evolution, people entertain far more exotic formation channels, like primordial black holes formed in the early universe. That idea is speculative but has active theoretical review and observational constraints. It's not the default explanation, but it's not off the table when an object truly refuses standard stories. Let's clear the biggest fear first, and be very blunt about it. A nearby, quiet black hole is not a cosmic vacuum cleaner waiting to swallow the solar system. Black holes don't have a magical pulling power. From far away, that gravity behaves just like any other object with the same mass. If you replace the Sun with a black hole of equal mass, Earth would keep orbiting almost exactly the same way. No sudden chaos, no instant doom. Gravity follows the same rules described by Newton and refined by Einstein. Distance matters, and we are very far away. And nearby in astronomy still means light years. That's trillions of kilometers. The nearest confirmed dormant black hole candidates are farther from us than thousands of stars we already live peacefully alongside. So in physical, everyday terms, there is zero immediate danger. But here's where things actually get uncomfortable. Not physically, but intellectually. The real risk is not what a black hole might do to us. The real risk is what we didn't know was there. For decades, our picture of the Milky Way was shaped by what was easiest to see: bright stars, explosions, glowing disks, violent events. We built theories around loud black holes, the ones feeding, flaring, and screaming in X-rays. Quiet black holes barely made it into the conversation because we simply lacked the tools to detect them. That means our mental map of the galaxy has had blind spots. If quiet black holes are common, and growing evidence suggests they are, then our neighborhood may contain far more invisible mass than we assumed. These objects quietly tug on stars, subtly reshape stellar orbits, and influence how star systems evolve over millions of years. Not dramatically, not explosively, just persistently. The final twist, and the road ahead. The phrase, "this black hole shouldn't exist," sounds sensational, but in a strange way, it's doing science a favor. It forces astronomers to slow down, double-check assumptions, and ask harder questions. Are our distance measurements accurate? Are we modeling stellar companions correctly? Are there formation pathways we've ignored because they're quiet instead of dramatic? This pressure has already paid off. Data from missions like Gaia have fundamentally changed the game. Instead of only seeing where stars are, we can now see how they move with astonishing precision. That motion becomes a map, a gravitational fingerprint revealing hidden mass. Some Gaia-flagged black hole candidates collapse under scrutiny. Others survive repeated checks, independent observations, and alternative explanations. And when they survive, they force theory to adapt. At the same time, completely different methods are adding independent clues. Microlensing surveys catch invisible objects by how they bend background starlight. Vanishing star programs search for massive stars that simply disappear without a supernova. Careful reanalysis of controversial cases, like Pound 1, reminds scientists that humility is part of progress. All of this points to the same conclusion. We are not discovering one impossible black hole. We are discovering the limits of our old assumptions. The scariest part isn't that a black hole appeared where it shouldn't. The scariest part is what that implies. That the galaxy is full of invisible objects we're only now learning how to notice. We are, quite literally, switching on new lights. Instead of mapping the Milky Way by brightness alone, we're mapping it by motion. Watching stars betray the presence of unseen companions. And as that map fills in, this impossible black hole will almost certainly lose its uniqueness. It won't be the anomaly. It will be the first one we noticed.